So Chris, are you ready for a virtual cup of tea then? You're going to be doing the virtual cups of teas. We've all got them. Thank you very much.
Ah,
We didn't know about the tea. We've got G&T.
Not quite a cup of tea. Sorry, I didn't realise tea was required.
Yeah.
All in favour of that one.
We normally have to drive. Yeah, you can drink. You can drink.
Yeah, I'm not driving anywhere afterwards.
Yeah. That's an advantage, isn't it? Doing these online.
Yeah, don't have to drive home afterwards, so it's fine.
We had our society's talk on Monday night, and we had 35 attendees, so we're more than we normally have on a day when we can all meet up.
Mm.
I can't say I can beat that. But, what are we on? We're on 20 or so at the moment.
18 at the moment, according to your.
So I will make you co-host now. And that will save if I can find it. Now we're on 20. I have problems arranging my screen. Oh, it's Mike. Oh, John's come in. Yeah, should be up to 21. There you go, Steve.
Well, no, still got no sound.
Well, now the background's gone on your T-shirt, Darryl.
Could be dandruff.
Yeah, Dan, I think I am now co-hosting because I keep getting notices up to admit people. So
it should be now. Yeah. Need to co-host. Yeah. So I just found your picture. I had to scroll along a lot of pictures at the top there. So yeah, welcome Martin, welcome Peter, welcome Paul, Paul and Sally, I presume, watching on the same device. It does take a while, I think, from the Zoom meetings I've seen before. We'd like to give a good amount of time to make sure everybody's in. There's John Jonas, yeah. I think most people are on mute at the time. Oh, we can see you. John's on mute. And Robin, yeah, one of the regulars, yeah, nice to see you. Sorry for not mentioning you. And here comes Bernie with a whole load of books behind it. Always looks good when you've got a bookcase as a backdrop, doesn't it? And a graduation photo. That's fine. And knitting is brilliant as well. Just shows how relaxed you can be.
Of course.
You might know it's the perfect time to do knitting.
It's ideal. The hands don't do the talking, so.
Yeah. It's all right. It will be more passive in a minute when Steve gets going. I'll give it till it's slowed down now. There's 23 of us here. I'll give it till 7:35. Have another sip of coffee.
Here's everybody.
Oh,
Yes.
yeah. Yeah. I'll have some beer in the shop. We even got some flowers I could get in the shop. Never mind the backdrop. No, yeah, the treasurer's not in yet though. I might just send him a message.
Give it as long as you like. My PowerPoint's just crashed.
Oh, okay, yeah. I'll score.
Hey, John, are you coming on this talk tonight? I'm on it. I'm on the Breckland one already.
Ignore here, Alan, at the moment. Just unmute Alan.
Oh dear.
There you go. I've just muted Alan. Are you having trouble joining? Yeah, maybe he's busy. Right, okay.
Is that chat that's come up?
Well, nice to look. Sorry I was a bit late. It's a challenge with my laptop. That's okay, Mario. I should be entertaining you, shouldn't I? Sorry. Yeah, so just I was telling a few people earlier that the ones who visit the hall and the observatory, obviously it's going to be a little while. I mean, we don't know when we're going to be able to go back. There's quite a few people that are keen to go back, and some people are very not keen to risk anything. Obviously, there's a big range of opinions of what we should be doing, and whatever the case, we've got to do things really safely. So we measured up the hall, and we found that we could get 18 places in the hall if they were spaced 2 meters apart in a hexagonal grid pattern, which isn't that many. I mean, it's possible that only 18 people will come because not many of us, but obviously if we get, so we'll then have to sort of have a system of booking places or something like that for the next talk, and that's July's talk. Because it's such a good speaker. If the Boris, in his wisdom, decides to reduce the spacing to 1.5 meters or something like that, we can obviously fit in a lot more people. But obviously, it all depends on the announcement that's coming next Thursday, I think. So, and it's similar with the observatory. You can't really fit many people in that because it's a bit of a tiny little shed type thing. You can only really fit, for those that have been there, you can only really fit 5 or so in there at any one time. It's probably safer given the surface contamination of this virus, or the unknown factor that we just have most people just going outside. After all, astronomy is an outdoor activity, isn't it? And ideal. It's also, it can be a nice solitary activity, but what we do is it's more of a social thing. So it can still be enjoyed outside. One person can go and bring telescopes and coffees out, etc. So we might be able to open like that. But it all depends on what is announced and what is possible. So that's with regard to opening. And the members among you, the ones that have subscribed and paid their subscriptions, Breckland Astro Society, there should be a newsletter going out every month for you to make up for the lack of lectures. And we're grateful to Chris Bailey for that, for getting them out. And anyone who wants to write a little piece for that, even a short notice, like a paragraph or something, or a photo they want to send in, can go to newsletter at brecklandastro.org.uk. And I think that'll be gratefully received for July's issue, because we're doing a monthly. Obviously, July's talk, I think Paul Becksmith is with us. He's watching. Paul and Sally are watching. We should have been having, I'm not committing to this yet, but if all goes well, hopefully Dr. David, or Professor David Southwood, our July speaker, will be willing to come to the July talk, but we've got to talk about that yet, so we may cancel. It depends on the rules, or if it's too risky or something like that. And therefore the AGM that we normally would have had in May, we'll give you a month's notice after that. And at the moment it's scheduled for August, the AGM. For those of you that are bothered about that sort of thing, it's usually a 5-minute job, isn't it? And while you're all here, any donations towards the small Zoom fees or speaker fees or general donations now can go on the website. They can be done on the little button at the bottom of the website. So if you go to brecklandastro.org.uk, there's a little donate button at the bottom. Steve kindly doesn't want a fee, that's very good, but of course a donation towards the campaign for Dark Skies on his behalf would be great. be good for us all. If see if we're generous enough to kind of put a suggested £2 or £2.50 or something in there, possibly a gift, a speaker gift fund as well, depending on what we get in there. PayPal do take a very small cut, unfortunately, but it's a very handy way of paying. I'm sure most people are used to doing that sort of thing online now. We've got to get with technology these days, haven't we? In terms of the sky, well, it just started raining, and that stopped here. The summer twilight to contend with, which obviously reduces everybody's visibility of things. But something Steve picked up on Steve's Facebook group was that there's a Venus occultation coming up in the daytime. It might be quite hard to see, but Venus is very bright if you've got a clear sky. And the thin crescent moon will be somewhere in the south or southeast. Southeastern sky, yeah, thanks. And right at the corner of it will be Venus, also in a very thin crescent phase. And the moon, you'll be able to see the moon's orbital motion around Earth as the whole thing moves across the sky. So if you can track that, that would be a nice opportunity. And it's around about 8:30 to 9 in the morning. Anywhere should be able to see that, provided the sky's clear. That's just a nice little thing that you can do. You can do many things in summer twilight when you've got a really bright sky.
Yeah. It's about 23 degrees from the sun, so you should be able to find somewhere where you can get a building to block out the sun, so you don't have the possibility of a nasty accident, and still be able to see the occultation. So with any luck.
Yeah, it's quite difficult. You always have to be aware of the sun, don't you? Yeah, it's a very good point. Essential. So if Andy were here, I think he's having trouble coming in. We may have done the lottery draw for those members who got lottery tickets, but we'll put that off till next week. So, are there any other? Oh, here he comes right at the last minute. Andy's coming in. So let's just wait until he comes in and we can see. I think he's having trouble joining. Unmute Andy now. I still have master control. So at least Andy gets away with not taking your money at the door and issuing you little lottery tickets. Let's see. Hi Andy.
Hello.
Hello. Did you want to do the BAS 100 draw?
Yeah, give me 2 seconds while I find stuff.
Okay. Dan, is it possible to turn your volume up at all? Right, I'm probably too far away from the laptop. Can you all hear me? Okay. Just a general shout out and thumbs up. Yeah. Okay, it should be okay. Some of you put a thumbs up. That'll do. Yeah. And Steve as well.
Is this loud enough for you?
That is fine for me. It's fine for me. I mean, I didn't have any issues. I didn't think it was a thing, but yeah, we've got to check. Yeah, I just had a message in the chat. Dan's it possible to turn your volume up? There we go. Yeah. So, yeah, I think, is there anything else to add? Right, we've got John Jonas here. What I should say is with Mick here, me and Mick have been going down the observatory and doing some maintenance, and we've got it all looking a little bit nicer and spotted a few things that need doing. So it's general maintenance things. And there was a picture that went up in the Facebook group about of me up a ladder, which generated a few controversial comments. I thought it was fine at the time. I looked across and with my hands on the dome like this, and I was on top of the ladder, and there was another ladder in the shot, and the whole thing looked really curious. It's like I was kind of not abiding by my own health and safety rules. And, I was trying to get some rust off the dome, these things. At the time, I think we were having a conversation of painting it up like R2-D2, like the one in, I think it's a Hochschule somewhere in Germany, where a chap who's a big Star Wars fan did that. Right. Andy, so if you can't find the tickets, that's no problem. We can go into introducing Steve. Microphone's off. So the talk, Steve said, is in 10 parts. So feel free, if you do have a really good burning question, if it's just an occasional question, that's fine, to type it in the chat bubble, which is I can see here, and probably so can Steve, and then so he'll answer that. Can you see the chat?
Yeah, I've got the chat. I can see the chat.
Good. So if there's a burning question that pops up, then you can just tend to that, and that's quite a nice way of quietly asking a question. We should really do that when we get back to actually physically meeting and holding up questions. Good way of doing it. Now,
well, if you go to reactions, you can also put up your hand.
Yeah, there are a few little actions if you explore Zoom, but I don't know if anyone's not a good play with Zoom yet. So yeah, there's a few Zoom points, finding the chat. We're recording, by the way, so
yep.
It doesn't take up much space, so we can record it and put it on the cloud. And so Steve, an author and astronomical author, creates a fun monthly newsletter. Steve Tonkin's Binocular Sky, I always watch that. And runs the website binocularsky.com, where you can link to anything. His latest book is Discover the Night Sky Through Binoculars, and he did the original one a good while ago. We've got a copy of it at the observatory. You can always borrow when things become more accessible, called Binocular Astronomy. And you can just find Steve Tonkin, just do a quick search, Steve Tonkin Binocular or something like that, and that will come up. So I've certainly heard of Steve. So, by the way, Andy, we're going to skip on to the talk now. That's
all right.
All right. So we can do the draw next month. I don't think anyone will be too bothered. Right. So
No, we'll do it after the talk.
Yeah. Have you got any other comments, Andy, on things like opening up? You probably missed all the announcements, but I generally just sort of said we'd still have to wait to decide before physically letting people.
Just the Federation of Astronomical Societies is sort of like seeing how other astronomical societies are going to sort of open up after all this sort of eases a bit, and we're going to sort of do our own thing and maybe sort of take some guidance from the Federation of Astronomical Societies. Yeah,
thanks. Yeah, it's good documents that came out from them. Okay, right. Aside from that little break, I was talking about binocular astronomy with Steve. So, Steve, finally, after a long wait, it's over to you to share your screen and start the talk. 10 ways the universe tried to kill you.
Okie doke. Before we get into that, one thing we noticed with other Zoom talks is if you're having trouble, if it's going a little bit clunky for you, if you turn off your own video, it reduces the amount of strain on your internet bandwidth, and it'll you can get a bit of a cleaner thing. The other thing is, if you're muted, which is usually a good idea anyway during a talk, if you do need to say something at any time, if you use the space bar, that actually acts like a transmit button or something, so it unmutes you temporarily. So that's just a few things we noticed. Right, so let's go into this. I need to do that as well. Come on. Right, do you have a screen in front of you which says 10 ways the universe tries to kill you?
Not quite yet. It takes a little while to come through. We do now.
You do? Jolly good.
I do anyway. Hope everyone else does.
Right, let me just minimize that. Okay. So what's this all about? Well, ultimately, I think what we're going to find out is the universe is a complete and utter, let's change that just in case you've got any youngsters in the background, use Shakespearean language. The universe is a vile, misbegotten wretch because as far as we know, obviously we're extrapolating from the sample size of 1, it's invented one way to create life. But there are literally thousands of ways it can get rid of it, which seems a bit of an imbalance, really. So in a sense, we're sort of lucky to be here. And what we're going to talk about tonight is just a few of those ways, some that interest me. There's so we're not going to be talking about COVID, you'll be pleased to know, or G. Young Trump or whatever his name is, you know, so trying to do something stupid to take us out, or other of our own stupidities. We're also not going to talk about space weather because that's actually a talk in itself. But a few of the things that interest me, and with a luck, we'll pick up a little bit of astronomy on the way. So that should, I hope, be okay. So we'll start off, if I can get this thing to move. Right, let's do it like that. There we go. Gamma ray bursts. And we'll take everything in the same sort of order so we get a sort of, you know, everything sort of fits together, as it were. So what are they? They are probably the consequence either of a supermassive star, probably a Wolf-Rayet star, collapsing to form a black hole, or 2 neutron stars combining to form a black hole. And that's been sort of confirmed by the LIGO and Virgo things last year. But what you get is in a few seconds, usually less than 2 seconds, they produce more energy than the sun will in its entire 10,000 million year lifetime. So they are massively powerful. But fortunately, they don't radiate in all directions. They have magnetic fields associated with them, which channel the beams. And so you get, on average, a 5-degree beam angle spreading out in 2 directions. And that's essentially how they work. And if you're in the beam, you have a problem. There has been suggestions that Earth might have been in the beam once before. We'll come to that in a bit. And there's also been suggestions they might account for what's called the Fermi paradox. And that was when Frank Drake estimated originally that there were about 20,000 communicating life forms or civilizations in our galaxy, but no one's ever found one. And possibly, you know, they only get so far and then they get clobbered by one of these things. Anyway, if one happened to us, it would, at an instance, it would destroy the ozone layer if one happened to hit us, if it one from our galaxy. It bombard one side of the Earth with lethal radiation, only one side, because it only lasts a couple of seconds. And the consequences of that would be you'd get mass extinctions, you would get then food chain disruption and ultimately starvation. So even if you were on the side that didn't get clobbered, you're probably going to starve to death. How nice. But remember, they're only a problem for planets in the beam. And if we start taking an idea of what the scale of stuff in our solar system, because we're going to keep having to come back to this, if we take, say, the sun as being something the size of one of those 16-inch lantern lampshades that used to be all the rage a couple of decades ago, the spherical tissue paper ones. If the sun was that size, the Earth would be a 4-millimeter pinhead over 40 meters away. And on that same scale, Pluto would be would be something like a mile away. And the nearest star on that scale would be North Korea, or if you prefer, Brazil, which are both about the same distance from us. So that's the sort of scale we're looking at. There's a heck of a lot of space. And as long as our little bit of space isn't within that 5-degree beam angle, we're fine. So that's useful to know. So we're not desperate there. So the important thing is, though, is how frequent are these things? Well, long bursts are thought to occur in a galaxy the size of Milky Way every 100,000 to 1 million years. But we detect them at least once a day from the universe, and that's long bursts. That's ones that last more than 2 seconds. When it comes to short bursts, which last less than 2 seconds, basically nobody has a clue because they're so difficult to accurately detect. But there are spacecraft up there, satellites up there, and if they detect gamma rays, they immediately communicate with Earth-based observatories, and basically says, stop what you're doing, point there, to try and get more idea of what these things are. I mean, they're still, yes, we know they're very powerful, but they're still very enigmatic. Have we actually been hit by one before? Well, possibly. As you probably know, there's been several great extinction events in our sort of 4.5 billion year history, or quite a lot less than that, so if we look at since the Cambrian explosion. But the Ordovician-Silurian extinction event, which is one that essentially took out the trilobites and so like, 445 million years ago, that was possibly, I think, a gamma ray burst, because they can't find evidence of anything else. I mean, it's pretty speculative. So we may already have been hit. That's actually, if it was, that's actually quite good news, because life survived. So, you know, it's not the end of everything. Okay, so what can we do about them? You may have your ideas about this, but the answer is nothing, because we won't know about them until they hit. Because gamma rays travel at the speed of light, information can't travel faster than the speed of light, so we can't have news of them before they arrive. So, hey, no point preparing for them, because there's nothing we can do. So what's the risk? Actually, because of how rare they are in our galaxy, and those are the ones we'd be concerned about, and the relatively narrow beam angle, it is infinitesimally tiny. So we don't need to worry too much about those, but let's move on to something a little bit nastier, which is magnetars. So what are they? Slow rotating neutron stars. So we're talking about things that rotate about once per second to once a 10-second. You've got something probably about, you know, the size of something like King's Lynn, or we've got here Ride, but it's got more mass than the sun. So it's a pretty odd beast in that sense, but it has like sort of star quakes on its surface, the equivalent of earthquakes, only star quakes, and they create powerful magnetic fields, and as they decay, they emit X-rays and gamma rays. So they're pretty good. The other thing is they're not, you know, with a nice little thing like a gamma ray burst, you've got nice sort of beamed emissions. Not this. These things are omnidirectional. So you've got omnidirectional, it's like an omnidirectional gamma ray burster, coupled with a huge electromagnetic pulse. And not only that, there's thought to be about 30 million of these things in the Milky Way. So they're pretty nasty and pretty, you know, someone said it's something like taking a cruise missile to a boxing match. You know, it's really, they're not fair. So they get us, well, beta rays, gamma rays, even if it's not enough to kill us, long-term radiation sickness, but also knock out communication satellites, almost certainly if one was close enough. I mean, they've already been affected by them, as we'll see in a minute. And if we knock out our communication satellites, we will have global economic collapse. COVID, lockdown, recession will be nothing compared to this. And that, of course, will lead to chaos. If you've ever been in a country which has undergone economic collapse, it's not pretty. I mean, most people know about Germany in the early 1930s, but I grew up in Zimbabwe, and I was back there when it had its last little nasty, where you took money out the bank and you went shopping immediately because 4 hours later it's going to be worth about half as much. It's a pretty nasty way to go. But the important thing, of course, is not what they could do to us, but we also need to know how frequent they are. Well, the first one was discovered in 1979, and it affected satellites in Earth orbit then, and we've been hit at least twice since then. The first one since then was August 1998, where the spacecraft near Schumacher, which was going to Eros, wasn't it, had to shut down to basically avoid being forcibly shut down by this thing, and that was from one about 20,000 light years away. And then about 16 years ago, we got hit by one 50,000 light years away, and it actually affected the ionosphere. It was actually detectable in our atmosphere. And the nearest one is a mere 9,000 light years away. And if you do your inverse square thing, it is going to be approximately 4 times as powerful as this one over here, the 1998 event. So they are potentially pretty nasty, and that's what we need to be careful of. So again, what can we do about them? This is when you might start noticing a sort of theme that runs through this talk. The answer is nothing, because we don't know about them until they hit. Okay, so what's the risk? The Armageddon risk is pretty small, actually, but it's a very, very high risk of satellite disruption. And this, along with space weather, and cosmic rays as well, actually, which we'll come to a bit later, causing people to take satellite resilience a lot more seriously than they did, certainly in the sort of 1970s when they were putting them up there. So it's tiny Armageddon risk. So let's move on to that next one, which is cosmic rays. You've probably seen this. This shot seemed to be doing the rounds a lot when Tim Peake was up there. Excuse me, on the space station. And what we're seeing here is you have a single particle coming in, but as it hits Earth's atmosphere, it causes a cascade effect. So what you get on the ground is an ellipse of basically high energy particles, radiation. So they are high energy, massive particles mostly, that originate from these, from hypernovae, which are like supernova of massive stars, or kilonovae, I think they call some of them nowadays. They, if we think what we're doing in the Large Hadron Collider is impressive, no. These things have energies millions or tens of million times greater than particles accelerated in the LHC. And what they do is they cause this secondary radiation when they hit the atmosphere. Give you some idea of the energy of some of these things. There have been a few of these detected now, but the first one that was detected, this thing had so much energy, you've heard of the God particle. Well, they called this one the oh my God particle. It was probably an iron nucleus, and it had the same energy, I reckon, as a tennis ball hit at full pelt by someone like Andy Murray serving. So it's just tiny little atomic nucleus having the same energy as something billions of times bigger. Obviously, because it was going a heck of a lot faster. So that's the sort of thing that is coming in. Now the particle itself that comes in probably won't affect us, and even if one did, we probably wouldn't notice. But this isn't the problem. The problem is they get the secondary radiation starts causing DNA deletions, so we get potential genomic instability. Not necessarily a bad thing. If genomic instability wasn't a thing, we'd all still be archaea or something like that. You know, we'd never have got beyond that sort of very, very simple single cell stage. So, you know, this is actually quite useful, but it usually isn't. That's the thing. They are normally we'd expect genomic instability to cause little mutations and stuff like that in cancers and all the rest of it. And indeed, these ones do. They also affect computer microchips. So one single cosmic ray can cause what's called a flip bit. So a 1 turns to a 0 or 0 turns to a 1. And the average at sea level on Earth is 1 error per 256 megabytes of RAM per month. So this isn't the only reason Windows computers are, you know, need rebooting so often, but certainly on spacecraft, the space station, they do need to reboot their computers a little more frequently than we do down here, because there's much higher probability that you're going to start getting corruption on the thing there. So, how frequent are they? Well, they're constant. Not only are they constant, they're constant even underground, so you can't actually escape them. So what can we do about them? Well, that said, it does actually help you live at low altitude. You get less or fewer of them if you live at low altitude. So that's a good thing we can do. But not everybody can do that. So you get people like aircrew and astronauts. And this is where it becomes a problem. Got here, the safe limit is 1 millisievert per year, which is equivalent to 7 16-hour flights at 10,000 meters. That's approximately the cruising height of a jumbo jet. Don't worry too much about what sieverts are. It's just a measure of radiation which takes into effect the intensity of the radiation, but also its potential ionizing effect in your body.
Steve, can I just pause you for a second? There's quite a lot of clicking coming from there. I don't know if you can see in the chat.
No, I can't actually. So I've got 2 screens up which aren't showing there. Hang on, I will need to shift screen.
An audio thing. That there's quite a bit of clicking.
From me?
Yeah. Well, it seems to be you're the only one that's unmuted. Yeah, so that's why I presumed it was you. But and yeah, it might somebody said here in the comments here, might be something catching a microphone or
I'll check
mouse click. That's all. It's probably you, given you're the only one who's not.
Yeah.
It just sounded like a kind of mouse clicking noise or something catching when you were moving, perhaps. So just something to be aware of.
Yeah. No, thank you.
That's what I'm going to interrupt.
No, I am actually clicking my mouse, so it could be that.
Okay. Right.
That
noise.
That noise.
That noise, yeah. It was when you moved the mouse. I think.
It's moving a mouse, right? I will put it on a different surface.
Right. And there was a question about part 2 as well in the chat.
Right. Let's get to the end of this, and we'll do that.
Yeah.
Right. Is that making a noise?
That's fine.
That's fine. Okay.
It then started again.
Then it's not my mouse.
Okay.
Right. I wonder what it is.
It really is the zip on your fleece, Steve. Touching the microphone.
Is it? Right.
Marianne, Richard's confirmed it. It looks like it is. Okay.
Okay. Well, I've pulled the zip down, so that should
a little bit of that, but yeah.
That should get rid of it.
Okay.
Right. Thank you for that. Okay. Just want to say, yeah, but aircrew typically receive about 3 times as much as the recommended safe limit. So they are at risk.
Yep.
Ah, where's it gone now?
It's still doing it a bit.
That's nowhere near it now. Right, hang on. Just hang
It's
on a
just on
moment.
the edge of your fleece. If you turn
Yeah,
your collar
hang
up
on.
and put it on the outside.
We're making him strip.
Well, you weren't expecting striptease as well, were you?
Know about that.
Right, sorry about that.
Hmm.
So weren't expecting a striptease as well, were you?
Better. That's it, I think. Good.
Right.
Right.
Right, let's carry on then. No. So, right, what were the questions so far? See if I can.
Yeah. About magnetars, Steve. It's about the latest. What's the latest research that it's responsible for fast radio bursts? It's going a bit off topic, maybe, but it's interesting.
Yeah, I that, but I haven't actually looked into it yet.
Hmm.
Well, my control screens are completely gone. Meeting control. It's not showing.
But yes, I heard that magnetars were responsible for the last large fast radio
Fast
burst.
radio bursts, yes.
Yeah, I heard about it.
But that they are not going to be likely to take us out, as it were.
Hmm.
I seem to be losing. All right, I've lost my control screen here. Never mind. Let's just get back onto this. Right. Moving on. Hypervelocity stars. So again, what are they? If you think back a few decades, people were talking about what's going on in globular clusters. Globular clusters are thought to have formed at the same time as the galaxy formed. So the stars in them should be old stars, which means they should be reddening. But what they actually found was that you had some hot blue stars in there, and they couldn't initially figure out what was going on with these. How can you have young stars in something that's as old as the galaxy? And so they initially just called them blue stragglers, the implication being they were sort of behind in their development. But the story doesn't end there, as we shall find out. So on the hypervelocity stars thing, what you get is probably a triple star system, which is moving a black hole at the center of a galaxy. And one star falls in towards a black hole, and you get a binary pair which recoils and is ejected, and it leaves the galaxy, and the binary pair merges, and that forms a blue straggler. And this is, in fact, how the blue stragglers form inside globular clusters. It's older stars merging together, another round of nuclear reactions. So what you effectively get is huge star, 1.6 million kilometers an hour, approximately. Intense gravitational disruption if one comes anywhere near us, and that will could then trigger cataclysmic collisions in the solar system. I mean, with such a tiny target in the scheme of things, that a direct hit is unlikely. But when we talk about what can cause intense gravitational disruption, all of a sudden the effective size of the solar system, which mentioning earlier, with our scale, with the sun the size of a big lampshade and Pluto being a mile away, suddenly it's gone from this 2-mile diameter to something like a 4 light-year diameter. Any star coming within that would give enough gravitational oomph, as it were, to disrupt the Oort cloud, which could send stuff down. So we we could have something like a repeat of the late heavy bombardment. It may already have happened, and we wouldn't know because it takes everything thousands or tens of thousands of years to get here. But it could cause cataclysmic collisions. How frequent are they? Well, we know 34 of these things, and there's another half a dozen possibles. The fortunate thing is none of them coming this way. And the nearest one is 70 light years away, and we would get approximately 675 years warning per light year. So, you know, if one was coming this way, yes, the people with the, you know, the end is nigh placards, yeah, they'd be right for once, but they'd have a heck of a long wait. And that's only, you know, for the disruption to occur. And then you've got tens of thousands of years after that before the stuff actually would start raining in on the inner solar system. So it's not a major issue that if we saw one. So, but what can we do about them? Well, nothing, but we can spend a long, long time worrying about them. Risk, because of the size of the target we are, even if we do expand our target area from you know, the pinhead of the Earth to something a few light years across, on that scale, we'd be talking about something maybe 5,000 miles across on that scale. What's the risk? Tiny. We're still this very, very tiny target in the major view of things. At least we can see them. The next thing we can't, and this is rogue black holes. These are postulated. So the idea is they're the result of a gravitational kick from black hole mergers, and they travel through intergalactic space several million kilometers an hour. They're invisible because they've consumed all the gas surrounding them after being thrown out of their home galaxy. And so we can only detect them because of their effect on the light emitted by things behind them. Again, massive gravitational disruption. If one came too close, you probably know about spaghettification. The idea about spaghettification, imagine you're going into a black hole, going in feet first. The gravitational gradient is so great that your feet would accelerate in faster than your head, and you'd sort of be spaghettified. Lovely. And become added to the black hole singularity, which is, of course, is what would happen to the Earth if one came close enough. But if it only came within a few light years, or on our scale, about 5,000 miles, disrupt the Oort cloud and send down an enormous amount of debris onto us. So how frequent are they? Well, the short answer is nobody has a clue. What can we do about them? You know the answer to this one already. Nothing. Risk. It's actually been estimated, believe it or not. It's tiny. The risk is 1 in, and that is 16 zeros. I just thought the number looked more impressive if I wrote it like that, rather than wrote it as just 10 to the 16. It is an absolutely tiny risk, but it is there, and given enough time, things that have very tiny probabilities do happen, as evolution shows us time and time again. Okay. At the other scale, we've got rogue planets, and they are exactly what it says. They are planet-sized bodies, either ejected from a star system. When the solar system formed, it is the case that almost certainly, or many more planets, some got to the sun and some got chucked out of the solar system altogether by gravitational interactions with the other, or they may never have actually been formed in a star system. It's perfectly feasible, in fact perfectly likely, that planets can form in interstellar space without actually anything getting to, coming to the size of a star nearby them. The important thing is they orbit the galaxy directly. And again, how will they get us? Well, it's exactly the same sort of thing we've been talking about before: collision with the Earth, disruption of the Oort cloud, and all that sort of thing. How frequent are they? Well, it's disputed. The short answer is nobody has a clue. The low estimate is that for every 2 stars in the Milky Way, there is one to the unassociated planet, one rogue planet. That's the low estimate. It's quite an error bar on this, because the high estimate is that it's about 100,000 for every star in the Milky Way. And the short answer is we really don't know. But they have been detected. They're very difficult to detect. They don't emit their own light. So the nearest one that was detected is this one, CFBDSIR 2149-0403, which is 130 light years away approximately. And this was discovered, well, its discovery was announced in September 2012. Can anyone remember what was about to happen, what was predicted to happen in some quarters on December 2012? Yep, the Mayan apocalypse, which has been associated with some really weird Fruit Loopery, associated with a postulated planet X, which is on collision course with Earth and all the rest of it. Of course, it's not going to happen, but this doesn't stop the conspiracy theorists. Yes, this one is coming our way, and in some Fruit Loop quarters there was this. Yes, you see, we were right. This is the one. It's coming this way. Well, hang on, guys. You're predicting the apocalypse in 3 months' time. This thing's 130 light years away. How fast do you think it's coming? But as I say, you should never let a complete ignorance of physics or mathematics get in the way of a not very good conspiracy theory. Anyway, what can we do about them? You already know the answer to this. It is this theme. It is nothing. Risk? Well, really not worth losing sleep over. Right, let's look at something a bit more speculative. If you read Jules Verne's book, or you remember Jules Verne's book of how they got human beings to the moon, it was a socking great cannon. And this is what Verne shots are about. Forget things like the now probably not so as dangerous as I thought it was going to be hypervolcano under Yellowstone National Park, which people were worried was going to sort of take out half the United States if it went up, or supervolcano. These are bigger. Old thick parts of Earth's crust are called cratons. And the idea is you get a volcanic buildup of mostly carbon dioxide gas, actually, underneath the craton, which can eventually build up so much pressure it's forceful enough to launch a huge amount of crust and mantle into a suborbital trajectory. Well, that's nice, but it's, it's suborbital, so it's going to come down somewhere. But then something else happens. The pipe through which all this magma and gas and stuff's been shot up is empty, so it collapses. As it collapses, you get a hypersonic shock wave, which hits the remains of the craton, pulverizes it with equivalent of about 120 energy equivalent of about 120 gigatons of TNT. So we're talking of something about 6 million times the power of the Hiroshima bomb. So that's quite a lot. And this will blast about 20 gigatons of debris into the atmosphere. Lava fills the hole behind. And then you get the impactor, which was knocked off into suborbital trajectory, if you remember, that hits somewhere else. Nice. How will it get us? Just like an incoming asteroid, but much, much less warning, because it's only gone in suborbital. No chance of seeing this thing weeks in advance or anything like that. But it's also much lower velocity, and so much, much less damage than is caused by would be caused by a similar sized asteroid. Okay. So how frequent are they? Well, they're postulated. They may never have existed. It has been suggested, certainly before the greater evidence came for a cometary cause for the Tunguska explosion, that Tunguska was one of these, and that possibly they might happen every few 100 million years. But ultimately, nobody knows, and it is possible that they don't even exist. So sorry if I've just waited the last few minutes of your lives. Let's talk about something that does exist. Galaxy collisions. So what are they? Exactly what it says on the tin. You get a number of galaxies, 2 or more, that collide and they interact. And you get massively strong star formation as the interstellar gases combine. So it's at least you get more possibility of more friends to communicate with. Unless there's direct interaction, though, between another star and our solar system, we could escape completely unscathed. Now, if we take our scale that we've been using down even further, so that the sun now becomes the size of a ping pong ball, spiral arms, stars the size of ping pong balls, scale separation is over 500 miles, about 900 kilometers. And even in the galactic core, the separation is 2 miles. I mean, this is similar to the sort of thing that you get with asteroids. People worry, about how do you get through the asteroid belt? The answer is easily. It's not like the computer games and Star Trek and all the rest of it. The mean separation of sizable asteroids is of the order of 1 million kilometers. So it's sort of like trying to navigate a speck of dust through a field of baked potatoes or something, where the potatoes are a kilometer or so apart. That's your scale thing there. And we've got enormous amount of space and gas and dust when galaxies collide, and not very much stuff that's likely to hit us. If there was a direct interaction with the solar system, then we're back to the stuff we talked about before. It's the gravitational disruption, and ultimately we could get another heavy bombardment. They're happening around us all the time. This is why I'm showing lots of pictures of the things, because we can see them going on all around the place in the sky. What can we do about them? Well, you know the answer to this as well. It's absolutely nothing. What's the risk? One is different. It is certainty. This is going to happen. Depending on whose data you take and analyze, M31 is due to hit us in round about 4.5 billion years, or we will hit it, the Andromeda Galaxy, and they will eventually merge to form an elliptical galaxy. I'm going to show a little video of this. You should get the sound through. Come on. I think it's firing up. Blimey, it's taking its time.
There we go.
Starting. I'm afraid the starting captions take quite a long time. Time scale bottom right. That's years from present. Well, that's one that, well, if we're still around, that one will get us. Right, let's move on. Asteroid strike. I'd like to read you something. Some of you probably know this. It's from Arthur C. Clarke's book, Rendezvous with Rama. Sooner or later, it was bound to happen. On June the 30th, 1908, Moscow escaped destruction by 3 hours and 4,000 kilometers, a margin invisibly small by the standards of the universe. On February the 12th, 1947, another Russian city had a still nearer, the second great meteorite of the 20th century, detonated less than 400 kilometers from Vladivostok. That's the Sokoti-Allen event, actually. You can get little bits of that, of the iron meteorite there. It's an explosion rivaling that of the newly invented uranium bomb. In those days, there was nothing that men could do to protect themselves against the last random shots from the cosmic bombardment that had once scarred the face of the moon. The meteorites of 1908 and 1947 struck uninhabited wilderness, but by the end of the 21st century, there was no region left on Earth that could be safely used for celestial target practice. The human race had spread from pole to pole, and so, inevitably, at 09:46 GMT on the morning of September the 11th, in the exceptionally beautiful summer of the year 2077, most of the inhabitants of Europe saw a dazzling fireball appear in the eastern sky. And it was brighter than the sun, and as it moved across the heavens, at first in utter silence, it left behind it a churning column of dust and smoke. Somewhere above Austria, it began to disintegrate, producing a series of concussions so violent that more than 1 million people had their hearing permanently damaged. They were the lucky ones. Moving at 50 kilometers a second, 1,000 tons of rock and metal impacted on the plains of North Italy, destroying in a few flaming moments the labor of centuries. The cities of Padua and Verona were wiped from the face of the earth, and the last glories of Venice sank forever beneath the sea as the waters of the Adriatic come thundering landward after the hammer blow from space. 600,000 people died, and the total damage was more than $1 trillion. But the losses to art, to history, to science, to the whole human race, for the rest of time was beyond all computation. A great war had been fought and lost in a single morning, and few could draw much pleasure from the fact that, as the dust of destruction slowly settled, for months the whole world witnessed the most splendid dawns and sunsets since Krakatoa. After the initial shock, mankind reacted with a determination and a unity that no earlier age could have shown. Such a disaster, it was realized, might not occur again for 1,000 years, but it might occur tomorrow, and the next time the consequences would be even worse. Very well, there would be no next time. 100 years earlier, a much poorer world with far feebler resources had squandered its wealth attempting to destroy weapons launched suicidally by mankind against itself. The effort had never been successful, but the skills acquired then had not been forgotten, and now they could be used for a far nobler purpose and on an infinitely vaster stage. No meteorite large enough to cause catastrophe would ever again be allowed to breach the defenses of Earth. And so began Project Space Guard. And Space Guard is actually an organization. It's taken its name from this, and quite a lot of the stuff in this bit of the talk actually comes from, with the blessing of Jay Tate, who's the director in Space Guard UK. When we get onto the actual effects and what we can do about them. So it's there, but this idea that we could get clobbered by an asteroid isn't new. It's not something that started, when they started doing the linear Lincoln near-Earth asteroid stuff or anything like that. Certainly, H.G. Wells wrote about a similar thing. One of his short stories involves asteroid impact on Earth. So it's something we've been aware of the possibility for some time and have taken pitiably little cognizance of the fact that we should be doing something about it. So what is an asteroid? Well, it's a lump of rock, traditionally anything between about 1 meter and 500 kilometers in diameter. So we're really looking at some pretty little stuff to some pretty big stuff. And the stuff that's really dangerous is stuff that's about 100 meters or bigger. Okay. if we take what we knew about the early solar system, the inner solar system, in 1800, the year before Ceres was discovered, we look here, that's what we've got. We've got the sun, the Earth and its moon, Mars and its two moons, and Mercury and Venus, and that's it. 100 years later, we've got these little dots here. They're obviously, the size of the dots isn't to scale. It's just the quantity and their relative positioning is approximately to scale. This red one here is one that crosses the orbit of Earth and is therefore worth watching. By 1950, the year of my birth, there's quite a few more and quite a few more red ones, you see. So again, you know, we're knowing about these things. By 1990, it's getting a little bit crowded. By 1999, it looks like this, and no point going any further because it's just going to be a sea of green and red. So, and there are, we now know many, many more. We do that. It is likely that most of the big ones, maybe all the big ones, have been detected, but you can never be absolutely certain about this, because obviously the big ones are the ones that are easiest to detect. You know, it's why dinosaurs were called dinosaurs. You know, there's some fearsome lizard, and that was because the big bones were easier to detect. So the big fossil evidence of big dinosaurs was discovered long before fossil evidence of small dinosaurs. But the ancient Greeks discovered fossil dinosaurs and realized that something was going on there. So how will they get us? Well, you can either have impact, which is like this, and it's melting, and then you get hydrostatic uplift, and then ultimately that collapses. So you get a crater with a little telltale hill in the middle. Or you get airburst. So your meteoroid, which is the body, comes in, get a fireball, comes through the mesosphere, and as it hits the stratosphere, it starts disintegrating, and this is what we get. So we know this happens because we need to know how frequent these things are. Well, Tunguska, the June 1908, was something, probably a comet nucleus, probably something in the order of about 100 meters in diameter, 100,000 tons, 15 megaton TNT blast. Compare that to the 20 kilotons of Hiroshima. Artist's impression up top here, actual photograph here. Away from the epicenter, a bit underneath which exploded, the trees were flattened outwards, but this is quite close to it. And here, the trees were left standing. They were just stripped of their branches. They were just basically, the branches were literally blown down, leaving the trees standing there. Reading eyewitness accounts of this, it's terrifying actually, though fortunately it's only a few sort of reindeer herders and that around there. But they're talking about things, people being blasted into trees, thrown around, bones broken. And it's just very, very fortunate. This wasn't a major city. Say the Sikoti Allen one, which was 1947, again, miles from anywhere. That was a potential city destroyer. Also, had it possibly about 18 months later, it would have appeared as a nuclear explosion in the Soviet detection thing, and they could well have thought they were under attack, and you know, Dr. Strangelove hits, as it were. Okay. Probably remember this date because that evening we were all going to be looking for an asteroid that was going to pass inside the orbit of Earth's geostationary satellites. And early in the morning, this thing hit. About the size of a big building, 11,000 tons, 500 kiloton blast. We're still talking something 20 times or 25 times the size of the Hiroshima bomb. Look at this. Turn your sound up, folks. It's much more impressive. This one's much more impressive with the sound up. Come on. Fortunately, there's a lot of security cameras around, and a lot of drivers in Russia at the time had dash cams, because there's a lot of accident scams going on, so they need to be able to prove that. So, but the result is that there's a lot of footage of this. So this is one of the most documented asteroid impacts that we've got, and it's, you know, it was only a little one. You could see the sort of damage there. Despite that, there were just under 1,500 people hospitalized, no fatalities, almost all of them lacerated by flying glass. Reason being, people saw a bright light explosion and, oh, wonder what that is, went to the window, and of course, light travels faster than the shock wave, and then the window got blown in. The heroine, I suppose, of the moment was a primary school teacher, and what she did was she saw this bright flash of light and thought, opportunity for nuclear drill, and got all her kids to go under their desks. And even though the classroom was absolutely covered in glass shards, not one child was injured. She herself suffered a lacerated arm, but that's a bit of foresight for you. So what if, let's try and put this in the scale of stuff we know. If Tunguska was London, black here is basically what was flattened in the blast size. So basically everything inside the M25 effectively would effectively be flattened. That's the sort of thing we're looking at. This is a 100-meter impactor. Of course, it would need to be a direct hit on London to have that effect. But this is the sort of thing we should be taking some sort of notice about them. So what can we do about them? And the answer isn't nothing. It has changed. There's quite a lot we can do about them. We could evacuate, but can you imagine trying to evacuate 10 million people? Where to? How? You know, it'd be absolute chaos. You could take the, I call the Bruce Willis Armageddon thing and destroy the thing, which is possibly one of the most stupid things you could do, because what you're doing is you are turning you're turning a single predictable impactor into a cluster bomb. You're not going to reduce the energy of the thing by doing that. Or you could deflect it, and that's where the clever money is going. And we'll come back to that in a moment. So let's look at a sort of actorial chart to see where this sort of thing fits in. Whenever you've got risks you need to assess, you can put the risks up here. So this is something. So this is something that takes 100,000 people's lives every 10 years. We class that as intolerable. If it's 10 people's lives every million years, well, that's tolerable. You're not going to spend a lot of money on it. And you have what's here called a national scrutiny line. And you're trying to get things as low as reasonably possible. Local scrutiny line. And this is what we need to try to get risks down towards. So if we take something like the Chernobyl reactor, which went off in 1986, that would have been about there then. Loads of money has been spent, and that's brought this down to about here. So it's not quite as safe as we'd like, but it's certainly a heck of a lot better than it was. Okay. You know, we're talking about 10,000 people every 10,000 years of risks, which is, some people would say, acceptable. Aircraft crash is actually quite high, and we do quite a lot about aircraft crash. Tunguska, if it hit a major city, would be down here. You see, it's actually not quite considered to be in the intolerable on this basis. A 1 kilometer impactor, on the other hand, much more of a menace, particularly if you start taking a tsunami threat into account. Then it really becomes can really become a problem there. So that's the sort of thing we're looking at. So the idea is to spend money to get stuff down here. Let's look at the UK's situation. If we just take this 1 kilometer impactor, we could expect one approximately every 100,000 years. we would expect it to kill round about 25% of the population. So that means UK casualties would be in the order of 15 million. We're still members of the EU, and the EU has a value on each of our lives, an actuarial value of what we're each worth. Depending on where you are in your economic productivity, we're anywhere between just under 1 million and just over 3 million worth. So I'm nominally retired, so I'm down this end. Somebody at the peak of their economic productivity will be there. So let's just assume an average of about 1.5 million per person. So that means the total cost, just actuarial value of life, just, is in the order of 22,500 billion quid. Puts what Rishi Sunak is spending on keeping people furloughed and that into harsh perspective in that sense. But the cost per year, if we divide that by the 100,000, is 225 million. This does not take into account things like the cost of property, heritage, business losses, or anything like that. This is just, when I say just, I shouldn't say just, the actuarial cost of human life. That means if we are spending less than this on mitigation, we're doing better than breaking even. So how much do we spend? The entire UK Space Agency expenditure 2018-2019, which is the last year I can get proper figures for, is 375 million. So it's nowhere, and of that, well, we actually don't do our own, mostly our own asteroid mitigation program or anything like that. We're part of ESA, and our contribution to ESA's asteroid mitigation thing works out at about 5,000 quid a year. I mean, it is absolutely pathetic. But obviously, this is because politicians think in terms of, you know, next election, not in long term. I'm not going to go about ADA. ADA is it's going to try and deflect part of a binary asteroid by crashing a spacecraft into it, 2022. The sound for this never works on this. But what SpaceGuard are coming up with is, and it's the same thing ultimately that they started hinting at in Rendezvous with Rama. The idea is to use technology we've already got. Now we know how to deliver stuff to asteroids. We've done it. We know also that we can make a weapon, because we made it before, which doesn't have an enormous blast, but has one hell of an amount of radiation pressure. And that is what called the enhanced radiation device, or the in the 1970s, the neutron bomb, designed to take out tank crews if Eastern Bloc tanks started rolling across into Western Europe without destroying too much property. Somebody once said, you know, it's the ultimate capitalist weapon because it kills people and leaves property intact, but it wouldn't actually leave property intact. It wouldn't be that harmful. So the idea is you have a two-part weapon, and the first bit is a small one which explodes quite close, but not enough to disintegrate. Remember, we don't want to disintegrate this thing, and it creates a crater. And then the bigger bomb goes off, and the radiation pressure from this enhanced radiation device is the thing that deflects it. You only have to deflect it a tiny, tiny amount, and it misses. If you remember the bit from Apollo 13, where, you know, they were worried if they didn't get the angle quite right, they could either burn up by coming in too fast, or they could skim off Earth's atmosphere. And again, if we think of the relative size of Earth, if you're a long way out, it is a tiny, tiny, tiny target. So we wouldn't have to deflect it very much. So this is where certainly SpaceGuard is trying to get government directed, because we've got all the technology. We just need to join it up. Nobody's ever tried any of these things before. You also get a load of quite silly things, I think. Laser bees, send up loads of little lasers on them and just fire lasers at the thing in the hope that the radiation will deflect enough. Yes, it could work, but you know, no one's even built the thing yet. Or plant a very heavy spacecraft next to it so it gravitationally deflects it. Yeah, there's the I think the Brian Cox idea, which is paint half of it white or something like that. Can you imagine going to paint an asteroid? I don't know how they're going to do that, because then so the differential radiation from the sun acting on each side would deflect it. Yeah, deflecting it is obviously the way to go, because you don't want to create a cluster bomb, and this is the way I think we've got the ability to do it. Right, sorry, got a bit serious on that one. But yeah, I think this one is important, and this is one we should all be trying to get our illustrious leaders to take more cognizance of. So, we may survive all of those cosmic attempts to wipe us out, and so far, obviously, we have. All 9 of those we've survived, but the universe got one little trick up its sleeve still: solar expansion. So this is the size of the sun as a main sequence star. There. This is the size of the sun when it becomes a red giant. Have a diameter of 2 astronomical units, which means it will have a radius of 1 astronomical unit. Definition of an astronomical unit: distance between the Earth and the sun. So if the Earth stayed where it was, the same orbit, then it would be on the edge of the sun when this happens. So this is effectively what's happening. You're probably aware the sun is this dynamic balance between gravity trying to pull stuff inwards and nuclear pressure trying to push stuff outwards. So it's held dynamic balance. And at the moment, we've got nuclear reactions going on in the core, and that is what's actually stopping the sun from collapsing under gravity. Ultimately, probably just over 2.5 billion years' time, actually, those nuclear reactions are going to start slowing down. When that starts slowing down, gravity is going to start winning. As gravity starts winning, the sun contracts. As it contracts, it heats up. As it heats up, a whole new phase of nuclear reactions start, and including some of the helium in the body of the sun. So the sun's now reacting throughout its body, and it expands enormously. As it expands, it cools, and as it cools, it reddens and becomes a red giant. But most people think the sun's going to get us when it becomes a red giant, which is round about 5.5 billion years into the future. That's actually not true. Because as it enters its red giant phase, it's going to lose mass. As it loses mass, Earth's orbital radius is going to increase. So we will no longer be 1 astronomical unit for the sun. So we may escape being engulfed by the sun. Isn't that lucky? So we're safe? Nope. We certainly will not be safe, because the universe is out to get us, as I said at the beginning, and it will. So in about 3.5 billion years' time, before it enters its red giant phase, it's going to double in size over about 500 million years and will become a subgiant. Its luminosity will double. As its luminosity doubles, Earth will become hotter than Venus is today. The surface of the Earth will become hot enough to melt lead, the oceans will disappear, the oxygen in the atmosphere will achieve escape velocity, and what can we do about it? You know the answer to this: it is nothing. Risk? It's going to happen. We've got about 2 billion years left, folks, and that's what it comes down to. But let's put that into some sort of perspective. Civilization started probably about 10,000 years ago. Homo sapiens has been a species for about 200,000 years. So this is actually quite a long time in our scale. So, final score. Humanity 9, universe 1. It gets us in the end. That's if we escape all the other things and don't wipe ourselves out in the meantime. But we still lose, obviously. And because, as I said right at the beginning, the universe is this vile, misbegotten wretch. And there we go. That's the
Well, thank you very much, Steve. Have a round of applause for that. Virtual round of applause. Thank you.
Let's try and get out of this.
Right, so I've just got a few things to say. You could spend a couple of minutes on a quick break if you want to think of questions, or you want to grab another tea or virtual coffee or something. If you need a bit of time to think of your questions, or a comfort break, very short one. But I can be, there's a few things to say. Andy has done the BAS 100 draw, and Nick Ladner got first, and John Jonas got second. So yeah, there you go. Yeah. And another little thing, sorry to detract from the amazing talk and go back into society admin for a second, but yeah, I think that was such a good talk. It's worth a small donation towards our, our Zoom costs and maybe speaker fees and a potential charity donation. So there's the donate button on the website. I'll remind you about that if you want to put a small donation in there. Yeah. So does anybody have? Oh, Andy says he was very honest in randomly selecting the draw. Of course, you did have to trust him. Yeah. Okay. So if you want to come back to Steve's rather scary, bleak lecture there that we all heard. So a few of you are unmuting your microphones already.
Is mine unmuted? Can you hear me?
I can hear John. Yes.
Okay.
John, do you want to go first? You're quite quiet there, John, but
hang on a minute. Your microphone any better?
That's better. That's better.
Okay,
Yeah, much better connection.
Yeah, right.
So yeah, fire away, John.
What?
Have you got a question, or are you just
No. I'm just setting it up to make sure.
Yeah, okay.
I'll think of a question.
Okay, right. Well, obviously, I've got. I could do with one to start. What was I going to ask? Yeah, if you add up all the risks. Yeah, everybody's still here. Yeah. You add up, Steve. If you add up all the risks, how likely are we to die of something from space in the next century? Any idea? Are you still there, Steve? I think Steve has disappeared.
Maybe he's gone to the loo.
Oh, maybe he's having his comfort break. Yeah. Well, okay. Yeah. We could, maybe if he's having a comfort break, we could just say a few more things. I mean, I'm just having a look there, and it looks like nicer weather for astronomy tomorrow. While we wait for Steve to get back. Oh, we've got a nice thank you. So hopefully we might be able to get out and do a little bit of astronomy tomorrow. It's a shame. I think Steve has just disappeared there.
Yeah. Well, what we could do, I mean, if I give you the question, could you ask him when he comes in?
Yeah. I think Steve is still.
I was going to suggest, given the 10 ways to get us killed by the universe, is it surprising that extraterrestrial life is very unlikely on those grounds alone? The chance of another civilization surviving any one of those 10 events will lessen the number of possibilities. Yeah.
Yeah, that's a good point, isn't it? Yeah, that's good. I think people.
What if we don't hear about anybody? Then they've been wiped out.
Yeah, I mean, if he's saying it's that unlikely, that was my first question I was going to ask him. What's the likelihood of, say, us surviving? Oh, here you go. Steve's coming back in I think he just. It said Zoom had crashed on my phone here, so it's all linked in. I think Steve is back. Or he very shortly is. He's just unmuting his microphone. It all takes a few seconds to ripple through.
Sorry about that. Zoom crashed.
Yeah, I saw a notification on my phone, Steve. Yeah. It's all right. Well, most of us are still here. We've had lots of people saying thank you on behalf of the other society, King's Lynn Society. That's nice. People are just generally getting a bit more comfortable. And yeah, so John had a question. You're still here, John. Do you want to ask it again?
Yeah, well, given the multiple ways that we can be wiped out, is it surprising that we haven't heard from any extraterrestrial intelligences? Because surely the chances of anybody else existing out there is also very slim as a result of them being whacked out by any of these events. Yeah.
Yeah, I said if we look at what Frank Drake came up with. He came up with a number of I think it was possible 50,000 communicating civilizations in a galaxy the size of the Milky Way. But when you think that we've got possibly 200,000 million stars, 50,000 is a very, very tiny amount. And we haven't actually surveyed enough stars to have even a probability of finding one of them yet. And if you then, since Frank Drake did this at about 1965, wasn't it? If you look at what we know now about what's there, so the parameters in the Drake equation, we know a lot of them more precisely. We know the error bars on others, and there may be at the top end 50. I think it's again of the order of 50,000. So it's not much difference to what Frank Drake said. But at the lower end of the probability of a intelligent communicating civilization in a galaxy the size of the Milky Way, the lower end of the error bar is 0.95. In other words, we're it. So, and again, putting this into some sort of context, we'd communicate by radio, yeah? That's the only way we can communicate out of here. We've had radio for just over 100 years. So our communication bubble is got a radius of 100 light years, which is, again, tiny compared to the size of the galaxy. And if you have someone on the other side of the galaxy who's there and their radio bubble is even 1,000 light years, we're nowhere near communicating with each other. I think realistically, the whole notion of interstellar communication it's pretty low. When we're just looking at the numbers and the sizes involved, and one of the things in the Frank Drake's equation is the time a communicating civilization lasts, and he had about 1,000 years. He was taking ages of civilizations throughout history, Roman Empire, things like that. I don't know how fair that is, because actually I think you've got to think really in terms of the whole species, because when a civilization goes, you don't lose all the advances other people have made. But it's just so slight a possibility, in my opinion. I know lots of people who would like there to be stuff new, and you get horrible planetarium programs directed at kids, say, yes, we'll have interstellar communication. No, you can't have interstellar communication. There's just absolutely no way. Anyway, sorry to be a downer on that one.
Yeah, it's okay.
It's like the whole thing's a downer, really, isn't it? That's what the talk's about.
Yeah, well, I'm such a miserable.
No, it's good. It's good that makes it more entertaining. I was going to ask a similar thing about adding up the risk to us. Because you're focused on if you added maybe another factor for the unknown unknowns. I don't know what's the best estimate of some space-related death of human civilization is.
Well, it's probably asteroids, actually. If we, you know, in the short term, it's probably asteroids. They think they've got everything over about 130 meters, which was a good thing. But of course, you don't know what you don't know. But then again, those are the ones that are easy to detect. The thing is, they're, you know, people think of asteroids as, you know, because when we look at them, you look at something like Ceres or Vesta, yeah, you can see it with binoculars. So I think, yeah, these are bright. No, they're not bright. They're approximately the same color as coal. And if one's coming from the direction of the sun, we've got no chance. You know, we won't see it until
it's still happening, isn't it? I mean, I've heard asteroids that have plonked into the sea with great force and been detected on seismometers.
Yeah.
It was shortly before the Chelyabinsk.
Yeah, and there was a fall somewhere in the Sahara a few years back as well. So we should be getting bits of that on the meteorite market sooner or later.
Yeah, where's David Bryant, the meteor collector? Yeah, he'll be on that. I think he's just
like a shot. Yes.
Yeah. No, he's just
Is there one called Apophis?
Oh,
Egyptian god of doom, which is due to, you know, is it 2032 or something? You call any dates on that?
2029.
Yes, it's. Oh, trying to remember. It's
pretty close.
Yes, it's coming close. As far as I'm aware of all the ones we know about, nothing hits for at least another 200 years.
I'll be okay.
Yeah. Yeah. Me too.
Well, that was. Are there any other questions? If people come back from their comfort breaks.
Suppose we could have a big tear, if that might be the way the universe is going to end. Obviously, the cold heat death of the universe is way in the future, but there are postulates that say space-time fabric might just tear apart and that could finish us off. It's a bit unlikely, but
yeah.
It's another one we wouldn't see coming.
Yeah, but who knows? I think really, yeah. Okay, if I can be serious again for a moment, the asteroid thing is the one it's the one we can do something about as well. So I think that's our short-term one. But really, we ought to be finding ways just to look after ourselves a little bit better, and each other. You know, I mean, I think COVID sort of brought it home to people that actually what's likely to wipe us out is stuff that's happening around us on a sort of human level, you know, and you know, great species extinctions, what we're doing to the environment and climate and all the rest of it are things which are probably much greater threat than most stuff from out there. If I can be boringly pessimistic for a moment.
And yeah, it's all related, isn't it? Non-astronomical stuff really dominates over the astronomical stuff. You could end up going into things like political destruction of the human race. But I somehow think that, like with the dinosaurs, near extinction, mass extinctions, a creature on intelligence will survive the nuclear winter or whatever we bring upon ourselves, and humanity will keep resurfacing once it's established, because that's, you know, a pattern of life. If you look through the whole history of life, it keeps coming back. Once it's there, it's persistent and it keeps coming back.
Yeah.
Which makes me think, you know, where are all the aliens and all that stuff. So yeah, it gets very deep, you know, but nobody knows the numbers, do they? I guess.
I've just seen a question come up on the chat. Although not an extinction level event, what will an X-class solar rejection do to us and our technology? If it does disrupt or depends on technology, could that cause a collapse of civilization? In principle, yes, but it's you've got two things going on. One is satellites, and but I mean this is the space weather thing. This is so this is a talk in itself. But the other one is, well, we know what happened when there was a relatively small CME hit back in the was it 70s, 1980s? I don't know, it all merges together when you get to my age, which took out the electric grid system in Quebec. And that was smaller than the Carrington event, which was the 1859 one, which is when telegraph was just getting going, and telegraph operators were getting shocks, and their nice wooden, nice wooden cabinets and that were catching fire and all the rest of it. And that's the sort of thing. And now we're much more dependent on this sort of thing. So yeah, it could take out grids, could take out satellites. And this wasn't taken seriously by the government until London 2012, when CME went off. Fortunately, it went off the other way. And it was pointed out that if that thing had happened 2 weeks earlier or 2 weeks later, it would have, direct hit on Earth. And London 2012 could not have happened because of how much of stuff would have been taken out by that. And all of a sudden, the government started getting a little bit concerned about this and actually set up a committee. The committee are all volunteers of people who want to do this sort of thing. Anyone want to guess how much they get paid? Nothing. Absolutely nothing. They all do it voluntarily, but the government is now taking resilience against space weather seriously, which at least that is a good thing.
Yep.
Well, I think going back to your talk, another thing, I think perhaps you could say humans 8, universe 2, in terms of the galaxy collisions, as well as the sun destroying us. But then, you're talking long term then, aren't you?
You see, I think it's potential that we could survive a galaxy collision, because you'd have to be really, really unlucky not to.
Oh yeah.
Because there's just so much. Because there's just so much space.
Yeah, it seems that it'd have to disrupt things somehow. With the bombardment of asteroids that you might get from a close pass, but the star. But there's also another good YouTuber called Dr. Becky who's done a video on that. Right? Are there any other questions? Anything else in the chat?
Well, I used to live in California for a few years back in the 70s, and clearing up my study, I found this book. It says, in time of emergency, nuclear attack, and natural disasters. So I decided not to throw it away because it might be useful. It might be, yeah. Time of emergency, yeah, you got all the organizations in the United States.
Yes, we had one here as well, didn't we?
Hey?
We had one here at the time of Reagan and Thatcher and that. It's called Protect and Survive.
Protect and Survive.
Yeah.
We've learnt something about the teacher in Chelyabinsk practicing her nuclear drill. That could save us one day. If you see an extremely bright flash of light,
get under the desk.
It's probably duck and cover.
Yeah, take cover inside the shelter. Take cover before the nuclear explosion occurs. You may be able to avoid fire injuries by putting out small fires or escape from large fires. That's ridiculous.
Well, I taught in Santa Monica for a bit, and I'm used to places here. Everywhere has a fire drill. They have fire drills. You also have earthquake drills.
Yeah.
So very concerned about that there. You get loads of tremors.
Well, I used to live close to the San Andreas fault. And yeah, a lot of the schools, all the kiddies were trained during the desk. Under the door jamb, anything like that. Yep. Oh.
Well, if there's no more, I'll just say thanks for a very detailed talk, especially the end. I mean, you sort of raced through the first 8, and I thought, oh, is it going to just be over really quickly? And then you really got going with 9, which was the meaty one, the asteroids section.
Yeah.
really the main risk, isn't it? I mean,
it really is, because it's I say it's the thing we can do something about.
Well, it's almost good to know. It's quite uplifting, really. I think it's just asteroids, and we're doing something about it. You can almost sort of put your faith in humanity on that one, because we're actually doing a good lot about it, and it's not been interfered with politically at the moment. So, like the climate change deniers. So yeah, at least there's that. So Steve, what are your other talks then? You alluded to doing a space weather one.
Well, I've got what have I got? I've got well, I've got the binocular astronomy one, of course.
Oh yeah, of course.
Why wouldn't?
Ben hosted that, didn't
Two eyes are better than one. Yeah. I've got things like Are We Alone? You know, which is on probability of finding life elsewhere. One called How Old Is It, which is about the age of the universe and how we know. Things like do one on the Star of Bethlehem, which is nice for Christmas. Usually raises a few hackles. Oops. There's and then one thing I've always been interested in is the way some people misuse astronomy. I'm thinking of people like it started with people like Hancock and Laval, you know, who start, you know, sort of making all sorts of things supposedly related to astronomy to say, you know, we've been visited by, you know, sort of ancient, or it's like this idea of ancient master races and stuff like that, from whom us poor humans had to learn and all the rest of it. And it's always wound me up. So I have a series of pseudo-astronomy talks. The earliest one just goes back to the people around about the time of Messier, who trying to faking evidence to try and make a name for themselves. It comes up to the 20th century. Then the you know, that lot around ancient master races, ancient advanced civilizations one is the next one. You know, did the ancient Dogon of Mali know about Sirius B? Well, no, they didn't. But doesn't stop, you know. Are Daily Express astronomy headlines ever right? No. And the last one is I take on the flat earthers. Because it's so easy. No, it really is an easy target. But it's just I don't like fake news, and it really annoys me when it hurts me when it's astronomy fake news. So there's that. But Dan, I'll send you my webpage which has got the talks on it. You can pick what you want.
Yeah.
If you want another one.
Yeah, I was just thinking, you know, I was reading something about ancient races, and I think Scientology came to mind with the 7,000-year-old race of aliens, and there was a crazy book there. Look at that for entertainment. I think we were in the chat talking about conspiracy theorists earlier. Yeah. So, yeah.
Yes, L. Ron Hubbard, wasn't it?
Yeah.
Yes.
Yeah. That's right. Yeah. And his wisdom. Yeah. Right. Okay. Well, thanks for all of your wisdom, Steve. There's just one last method.
Yeah, Bernie wins the bookshelf prize.
Bernie. Yeah. Okay. Yeah. Look at the best box. Yeah. That's it, Bernie. You've won. Okay. Right. Brilliant. Okay. Well, cheers, everyone. Thanks for coming.
All right. Thanks for inviting me.
Thank you.
Have a good weekend, everybody, and be safe.
Nice weather. Oh, we've got clapping. Yeah, find a clap icon.
Be alert. Be alert.
And just say, if you want it again, you know, Stargazers Lounge is doing their Stargazine Sunday night talks.
Yeah, I heard.
Yeah, I'm doing this one again on Sunday. So.
Well, we've recorded it, so we'll find out what to do with the recording as well. So, cheers. Right.
Okay.
Yeah.
Well, thanks for having me, and as you can probably tell, I enjoy this talk, so it's nice to do it.
Pleasure. Yeah, it's good fun.
Hey, guys.
Great. Thank you very much, everyone.
Yes,
Right.
thank you.
Thank you.
Very good talk. Yeah.
Right, you go first.
Many thanks from the interlopers to your talk.
Oh, that's all right. I had to ask you.
John did send his apologies, but he's got problems at the moment.
Okay, yeah, that's fine. Yeah. Yeah. Right. You're all
Cheers, Dan. Good to see you again.
Yeah.
Thanks,
you.
everybody.
Yeah.
Well, clocking out.
Bye, Marianne. Yeah.
Leave the meeting. There we go.
Bye-bye, Dan.
Bye, Ruth. Yeah, hope to see you in person again soon.
Yes.
See what we can
Maybe
do
next month.
Yeah, hopefully next month. Yeah.